Welcome back to lecture 2 of acids and bases. So in this lecture, we're going to continue our discussion and start with how to solve problems that involve weak acids. So we are talking about weak acid equilibrium. So the problem solving approach starts with writing the balanced equation, writing the expression for the acid ionization constant, defining X as the change in concentration. And then constructing a reaction table, finally making assumptions and substituting values into Ka expression and solve for X. Finally, check the assumptions are justified. So here the notation system generally uses molar concentrations are indicated by the brackets. And whenever you have a bracketed formula with no subscript, it indicates that it's an equilibrium concentration. And the assumptions are that H3O plus from autoionization of H2O is negligible. Remember that because this is because of the weak acid. And a weak acid has really small Ka, so its initial dissociation is negligible, so which means that the initial concentration is the same as that of the original concentration, its equilibrium concentration. So let's start with the first problem. So what is given here? You have phenylacetic acid, simplified here as HPAC, builds up in the blood of persons with phenylketonuria, an inherited disorder that if untreated causes mental retardation and death. A study of acid shows that the pH of 0.12 m HPAC is 2.62. So what is the Ka of the phenylacetic acid? So first things first, let's write down the equation. So we are talking about HPAC plus H2O. So this under dissociation creates PAC minus plus H3O plus. So let's write down the expression for Ka. We know that Ka removes the H2O value. So it's the concentration of PAC minus times H3O plus over the concentration of HPAC. So that's the concentration, the equation for Ka. Now the assumptions here are the same. So we assume that the H3O plus from the H2O is negligible. And we use the given pH to find the H3O plus, which equals the PAC minus concentration and also the dissociation of HPAC. And the initial concentration stays the same. The main reason is because HPAC is a weak acid. So how do you calculate the H3O plus concentration? So because the dissociation is really minimal because it's a weak acid, the equilibrium concentration of HPAC is equal to the HPAC concentration, the initial concentration of HPAC. So the initial concentration given here is 2.62. So the initial concentration given here is 0.12 m. And let's consider that the concentration of HPAC here is 0.12. Now we need to know the H3O plus concentration here. And we notice that when we calculate the H3O plus concentration, that will be the same as the PAC concentration because each of them are 1 mole each. So now the given value for pH is 2.62. So we know the pH formula is negative log of H3O plus is going to be 2.62. So how would you calculate H3O plus here? So H3O plus becomes negative. So the minus sign goes here. So when the log goes to that side, it becomes 10 to the power. So this becomes 10 to the power of negative 2.62. So H3O plus, the value is this one. So that concentration, when you calculate, becomes 2.4 times 10 to the power negative 3 m. So which is much greater than the H3O plus in water. So which means that there is a certain amount of dissociation that's happening here. Now the value is taken here. So the first thing that we need to know is let's draw the reaction table first. So how would you draw the reaction table? Again, use the same principle that you did in the equilibrium, in the concepts of equilibrium. So first write down the reaction right here. So the equation is HPAC plus H2O becomes PAC minus plus H3O plus. Now, again, the idea here is there is an initial value, there is some change, and the final value, which is the equilibrium value. So initially HPAC has a concentration of 0.12 m, and this is H2O plus is not counted. So we consider these two to be 0, 0 each. So the change here is this becomes negative x, which means that there is a certain dissociation of HPAC, which causes an increase in PAC minus and H3O plus. So let's consider that as plus x and plus x. So at equilibrium, HPAC concentration will be 0.12 minus x, PAC is x, and H3O plus is x. So we calculated that the x value here is the H3O plus concentration is 2.4, so which means that x is nearly equal to, so 2.4 times 10 to the power negative 3 m. Now, to calculate the HPAC concentration at equilibrium, so that value is 0.12 minus x, so which is going to be 0.12 minus 2.4 times 10 to the power negative 3 m, so which is nearly equal to 0.12 m. So when you calculate it, you find that that value is nearly equal to 0.12 m, because this is really negligible value, so we can remove that part out. Now let's take into consideration the formula for Ka. So from this we can also rule that this x value is also equal to the PAC minus concentration and also equal to the H3O plus concentration. So we have everything that we need. So the formula for Ka is PAC minus times H3O plus over the concentration of HPAC, so which is equal to, so 2.4 times 10 to the power negative 3 times 2.4 times 10 to the power negative 3 over 0.12. So that value gives about 4.8 times 10 to the power negative 5. So this is the value of the acid dissociation constant for the given phenyl acetic acid. So checking the assumptions whether our answer is correct or wrong. So from the H3O plus concentration, so we can calculate the H3O plus from H2O, and we can also calculate the dissociated amount, so which is about 2%, which means it's less than 5%, which means that our assumption here is justified. So use the same principle here and pause the video right here and try to solve this problem. So what is given here, you have propanoic acid is a carboxylic acid whose salts are used to retard mold growth in foods. What is the H3O plus of 0.10 m HPR, and they have given us the Ka value. So notice that H3O plus becomes x here. You have every other value that is given. Notice that the HPR concentration is nearly equal to the initial concentration of HPR. The equilibrium concentration is nearly equal to the HPR initial concentration, which is 0.10 m. And they have given us Ka. So the Ka value is already given, so which is 1.3 times 10 to the power negative 5. So how would you do that? So notice the formula here is HPR plus H2O gives you PR minus plus H3O plus. So if this is the reaction, so this is the initial, change, and equilibrium. So initially there is a concentration of 0.10 and this is dash, so 0, 0. And the change here is negative x, so which means both of these become plus x and plus x. And the equilibrium value is 0.10 minus x. This value becomes plus x and plus x. So the Ka value is given. So the formula, so Ka formula becomes the PR minus concentration times H3O plus over HPR concentration. So which when calculated becomes x times x divided by HPR. Notice that this is nearly equal to 0.10, so we can write that this is 0.10. So the Ka value from the formula, from the data here, is 1.3 times 10 to the power negative 5 equals x square by 10. So x square becomes 1.3 times 10 to the power negative 4, and x becomes square root of 1.3 times 10 to the power negative 4. So that x value here becomes 1.1 times 10 to the power negative 3 m. So which is equal to the H3O plus concentration is equal to the PR minus concentration is equal to 1.1 times 10 to the power negative 3 m. So this is how you can solve weak acid equilibrium problems. Next, let's talk about concentration and the extent of dissociation. So the percent of the acid dissociated is equal to the amount of acid dissociated, the concentration of the dissociated acid, over the initial concentration times 100. So as the initial acid concentration decreases, the percent dissociation increases. So which means that there is a decrease in, so a decrease in the initial concentration means there is a decrease in the dissociation, which means that the H3O plus, so there is a decrease in all of these values, causing a shift towards the products, which is the main reason why acid generally undergoes dissociation. The main reason is because H3O plus and A minus, both of them are weak, so which means that the product will be favored. So which means that they always go towards the weaker side. So the fraction of ions present increases even though the actual dissociation decreases. So let's take an example problem right here. So in 2011, researchers showed that hypochlorous acid generated by the white blood cells kills bacteria. Calculate the percent dissociation of 0.40 m HClO and 0.035 m HClO with a Ka value of 2.9 times 10 to the power negative 8. So what is the formula for percent dissociation? So that is the dissociated value, so which is HClO dissociated over HClO initial times 100. So this is the percent dissociation of HClO. Now the initial value, to calculate the HClO dissociated, so we might have to calculate the actual H3O plus concentration. So let's take the idea here that the amount of HClO dissociated is equal to the amount of H3O plus ions created, which is also equal to the ClO minus ions that are created. So to calculate this, we consider this to be X, and the value of Ka is already given in the formula, which is 2.9 times 10 to the power negative 8. Notice that here the Ka value is really small, which suggests that this is a really weak acid. So which means now, taking into consideration the formula for the HClO degradation, so HClO plus H2O gives ClO minus plus H3O plus. So now the formula for Ka becomes ClO minus times H3O plus divided by the concentration of HClO. Now taking into consideration the values that are given, so we consider these two values to be X, and this value is already given in the formula, which is the initial concentration is also nearly equal to the equilibrium concentration of H2LO. The main reason mainly is because this is a weak acid, so that value is 0.40 m. So now write down the value for Ka, so which is 2.9 times 10 to the power negative 8 equals, so X times X over 0.40, so which is x square by 40 equals 2.9 times 10 to the power negative 8. X square becomes 2.9 times 10 to the power negative 8 times 40. So X becomes square root of 2.9 times 10 to the power negative 8 times 40. So that X value here so becomes 1.1 times 10 to the power negative 4 m. So which is equal to the amount of dissociated HCl. So this is the actual amount of dissociated HClO present inside the concentration of an acid. So next one that is given here is this concentration of HClO. So the exact same problem, but in turn we change the denominator to 0.035. So the value becomes 2.9 times 10 to the power negative 8 equals X times X over 0.035. So this becomes x square by 0.035 equals 2.9 times 10 to the power negative 8. I'm really sorry, this is 0.40. So x square becomes 2.9 times 10 to the power negative 8 times 0.035. X becomes under root 2.9 times 10 to the power negative 8 times 0.035. So which when calculated becomes 3.2 times 10 to the power negative 5, which is also equal to the amount of dissociated HClO. So these are the two values. So this is the B when the concentration is 0.035 m HClO, and the one that is, so this is A, which is 0.40 m HClO. So this is how you can solve problems. Next, let's talk about polyprotic acids. So polyprotic acids are acids that have multiple protons, more than one ionizable proton. They are generally called as a polyprotic acid. Best example of that is the phosphoric acid. So phosphoric acid has 3 ionizable protons, but the idea here is to remember that as the dissociation occurs, the actual strength of the acid starts decreasing rapidly. So which means that each ionizable proton, as it goes away, it decreases the actual acid dissociation constant to a really small value. So the first proton has a value of 7.2 times 10 to the power negative 3. The second proton has a value of 6.3 times 10 to the power negative 8. And as you go towards the third proton, you start noticing that that value is 10 power negative 13, which means that anything after the first dissociation is generally neglected. The main reason is because it's negligible. Other forms of these acids, you have oxalic acid, which has 2 ionizable protons, sulfurous acid, which has 2 ionizable protons, phosphoric acid, which has 3 ionizable protons, arsenic acid, which also has 3 ionizable protons, carbonic acid with 2, and hydrosulfuric acid with 2 ionizable protons. So this is the idea behind the problem. Now let's solve a problem. So ascorbic acid, known as vitamin C, is a diprotic acid which has 2 ionizable protons here, and they have Ka1 and Ka2 values found in citrus fruit. Calculate the H2S concentration, HASC minus, AS2 minus, and the pH of 0.050 m H2ASC. So now we need to first write the actual equation. So there are 2 ionizable protons in here, so which means that you have H2ASC plus H2O results in HASC minus plus H3O plus with the Ka1 value of so with the Ka1, which formula becomes HASC minus times H3O plus over H2ASC, which equals to 1.0 times 10 to the power negative 5. Now let's take the second acid, so which is HASC minus. Again, let's try dissociation, which becomes ASC minus plus HASC2 minus plus H3O plus. Again, Ka2 here becomes ASC2 minus times H3O plus divided by HASC minus. So which values here? The given here is 5 times 10 to the power negative 12. Now considering the equation, so they have asked us to calculate the pH of this particular amount of acid. So to calculate that particular amount of pH, so let's first write down the reaction table for the first reaction. So you have H2ASC plus H2O gives HASC minus plus H3O plus. So you have initial, change, and equilibrium. So this concentration, the initial concentration is 0.050 m, and this is 0 and 0. So the change is negative x. So let's consider that if that is 1, so this becomes plus x. and plus x. So this value becomes 0.050 minus x, and this is x and x. Now notice that this value, because x is going to be k value is really small, we can assume that this value is nearly close to 0.050. So from this, using the Ka1 formula, which is HASC minus times H3O plus over H2ASC becomes x times x over 0.050. Ka1 is 1.0 times 10 to the power negative 5 equals x square by 0.050. So x square becomes 1.0 times 10 to the power negative 5 times 0.050. So x becomes under root 1.0 times 10 to the power negative 5 times 0.050. Now this value of x becomes 7.1 times 10 to the power negative 4 m. So which is also equal to the concentration of HASC minus and also equal to the concentration of H3O plus. Now notice that this is the concentration of the second part of the acid. For the second reaction, we need the concentration of HASC minus. Now write down the reaction table for the second part of the acid. So you have HASC minus plus H2O becomes ASC2 minus plus H3O plus. So you have again initial, change, and equilibrium. So the initial concentration is 7.1 times 10 to the power negative 4, and this becomes 0 and 0. The change is negative x, again plus x plus x. So this becomes 7.1 times 10 to the power negative 4 minus x, and x. So because this value is negligible, so we can write that this is nearly equal to 10 to the power negative 4. Now let's consider the Ka2 equation, which is ASC2 minus times H3O plus divided by HASC minus. So which is also equal to 5 times 10 to the power negative 12. So ASC2 minus is again x times x divided by 7.1 times 10 to the power negative 4 is equal to 5 times 10 to the power negative 12. So x square by 7.1 times 10 to the power negative 4 equals 5 times 10 to the power negative 12. X square becomes 5 times 10 to the power negative 12 times 7.1 times 10 to the power negative 4. So x becomes square root of 5 times 10 to the power negative 12 times 7.1 times 10 to the power negative 4. So that x value here is going to be really negligible. So which means that this value, the value that you get from H3O plus from the dissociation of HASC minus is nearly negligible. So we can only use this value directly that you got right here to calculate the pH, so which is the H3O plus concentration. So pH is negative log of H3O plus, so which is going to be negative log of 7.1 times 10 to the power negative 4, so which becomes equal to 3.15. So this is the pH of the given amount of acid. So this is how you can calculate the dissociation values using the acid values. So let's get into the next topic, weak bases. So just like weak acids, we can also write down the base dissociation or the base ionization constant. So we know that the Bronsted-Lowry base is a species that accepts a proton. So for a weak base that dissolves in water, we can write that the base plus water becomes BH plus OH minus. So because of this equation, we can write the Kb, which is the base dissociation constant, which becomes BH plus times OH minus divided by the concentration of B. So note that no base actually dissociates in the solution, but ions are produced when the base reacts with H2. So what happens here? is that the two pair of protons are generally, there is a obstruction of the proton, so which means that the lone pair of electrons binds to the hydrogen, resulting in a 3 lone pair OH minus with a positively charged ion. Now the Kb values of some molecular amines are given here. So most commonly we use amines as a source of values for Kb because most of the weak bases are ammonia or derivatives of ammonia. For example, diethylamine is the highest one, with aniline with the least value of Kb. So let's solve a problem. So what is given here? Dimethylamine is a key intermediate in the detergent manufacture, has a Kb of 5.9 times 10 to the power negative 4. What is the pH of 1.5 m? CH2 3H3 taken twice, NH. So you have CH3 taken twice, NH, plus H2O, which becomes CH3 taken twice, NH2 plus OH minus. Now write down the equation for Kb, which is going to be CH3 taken twice, NH2 plus times OH minus divided by concentration of CH3 taken twice, NH. So the Kb value right here is 5.9 times 10 to the power negative 4. So if we consider this as X and X each, and this is the initial concentration is given right here. So let's write down the reaction table here. So this is the initial change, so equilibrium. So the initial value here is given as 1.5 m. So this is 1.5, 0, 0. So this is negative x plus x plus x. And that value is 1.5 minus x, and x. So because this value doesn't change much because it's a weak base, so which means that this value is going to be nearly equal to 1.5. So from the Kb equation, so substitute the values into the Kb equation. So Kb value becomes x times x divided by 1.5, which equals 5.9 times 10 to the power negative 4. So x square becomes 5.9 times 10 to the power negative 4 times 1.5. So x becomes under root 1.5 times 5.9 times 10 to the power negative 4. So that x value becomes 3.0 times 10 to the power negative 2 m. So which is also equal to the concentration of OH minus. Now the idea here is to first find POH. So POH becomes negative log of OH minus. So which becomes negative log of 3.0 times 10 to the power negative 2. So which becomes 1.52. So this is the value of POH. Now to find pH, we know the formula is 14 minus POH, which is going to be 14 minus 1.52, so which becomes 12.58. So this is the value of pH. So this is how you find the pH. So first find the POH when you have weak bases, find the OH minus value, calculate POH and use the formula pH equals 14 minus POH, and then finally find the pH value. So that is how you can solve the problems. Next, let's talk about the anions of weak acids as weak bases. So notice that the anions of weak acids often function as weak bases. So the anion right here is also going to act as a weak base. So which means that the reverse reaction can also be considered as Kb. So the solution of HD is acidic while the solution of A minus will become basic. So which means that here, because the anion is the weaker side, the reaction will always favor the side which is much more gonna be acidic. So which means that it favors the side which is weak. So HF here is a weak acid, so this equilibrium lies to the left. So which means that the HF concentration is much greater than F minus, but the H3O plus concentration is much greater than the OH minus, so therefore the solution is acidic. So now let's find the relationship between Ka and Kb. So notice the reactions right here. So let's take the acid dissociation reaction, which is Ha plus H2O gives A minus plus H3O plus. So how do we calculate this? You have H2O. So A minus gone, Ha gone. And you notice that the reaction looks much more familiar. So it becomes H3O plus plus OH minus. So if you remember that this equation looks familiar, so this is the equation for the autoionization of water. Notice that the equation that we use here is Ka, and for this is Kb. So we can write that Kw is the product of Ka and Kb. So Ka times Kb equals Kw. So how can we write this? So let's take the equation for Ka here. So the Ka equation here becomes A minus times H3O plus over Ha. And the equation for Kb becomes Ha times OH minus divided by A minus. So A minus gone, Ha gone, so which equals H3O plus times OH minus, which is equal to Kw. So this is the reason why we write the equation Ka times Kb equals Kw. So let's take an example. So sodium acetate has applications in photographic development and textile dyeing. So what is the pH of 0.25 m NaAC at 25 degrees centigrade? And Ka of acetic acid is 1.8 times 10 to the power negative 5. So the equation becomes AC minus plus H2O becomes HAC plus OH minus. So from this we can write the formula for Kb, which becomes HAC times OH minus over AC minus. So the Ka value is given for acetic acid. So let's find out the Kb value. So we know that Kw equals Ka times Kb. So Kb becomes Kw by Ka. So Kw is 1.0 times 10 to the power negative 14 over Ka value is given as 1.8 times 10 to the power negative 5. So when you calculate that, that gives you a value of 5.6 times 10 to the power negative 10 m. So this is the Kb value. Now let's take this equation and write down the reaction table. So this is the equation that we have. So now let's write down the reaction table for this. So we have initial, we have change, and we have equilibrium. So the initial concentration is given as 0.25 m. So we can write this as 0.25, and this is dash 0 and 0. So the change is negative x, so this becomes plus x and plus x. So this becomes 0.25 minus x, x and x. So this becomes nearly equal to 0.25 because x is negligible. So we can write that Kb, the formula is HAC times OH minus over AC minus, so which becomes equal to 5.6 times 10 to the power negative 10. Now substitute the values. That becomes x times x by 0.25 equals 5.6 times 10 to the power negative 10. So x square by 0.25 equals 5.6 times 10 to the power negative 10. So from this we can write x here square root of 0.25 times 5.6 times 10 to the power negative 10. So that x value becomes equal to 1.2 times 10 to the power negative 5 m, which is also equal to the concentration of OH minus. But in the problem, it's given that we have to find the pH. So again, first find pOH, which is going to be negative log of OH minus, which is going to be negative log of 1.2 times 10 to the power negative 5. So that value becomes 4.92, so which is the POH value. So the pH becomes 14 minus POH, which is going to be 14 minus 4.92, so which is going to become 9.08. So this is the pH of that particular solution of sodium acetate. So this is how we can solve the problems. Next, let's talk about the acid strength of non-metal hydrides. So non-metal hydrides are generally acidic. Their acid strength generally depends on the electronegativity of the central nonmetal, which is the E, and also the strength of the EH bond. So across a period, this acid strength increases. The main reason is because there is an increase in the electronegativity and also an increase in the hydrogen bond, so which results in the increase in the acidity. Down a group, the acid strength increases the length because the length of the EH bond increases down the group and its bond strength therefore decreases. So in the period, electronegativity increases, so acidity increases. In the group, bond strength decreases, so acidity increases. So next, let's talk about the acid strength of oxo acid. So all oxo acids have the acidic hydrogen bonded to an oxygen atom. So the acid strength of an oxo acid depends on mainly two things: the electronegativity of the central nonmetal and the number of the oxygen atoms around the central nonmetal. So for oxo acids, the same number of oxygen atoms, with the same number of oxygen atoms, the acid strength increases as the electronegativity increases. And for oxo acids with a different number of oxygen atoms, acid strength increases with the number of oxygen atoms. So for example, when you take iodine, bromine, and chlorine, there is a high increase in the acidity with higher increase in the electronegativity because all of them have the same number of oxygen atoms. But as you notice that there is an increase in the oxygen atoms connected to the central nonmetal, there is an increase in the acidity. So the number of oxygen atoms increases the acidity of the atoms. Next, let's talk about hydrated metal ions. So some hydrated metal ions are able to transfer hydrogen H plus to H2O. These metal ions will form acidic solutions. When you consider a metal Mn plus H2O, this can become M of H2OX with a charge of N plus. So the Mn plus must be small and it should also be highly charged so that it will draw enough electron density to the oxygen hydrogen bonds for the bound H2O molecules to release the H plus. So this molecule still react the same way as that of an acid. They lose a particular proton, resulting in H3O plus formation and resulting in the original molecule. So this is the diagram that here shows here is the acidic behavior of Al3 plus ion, which has an aluminum hexahydrate ion bonding with a H2O molecule, loses a particular proton, and that loss of a proton results in a changed molecule, a complex molecule. Next, let's talk about salts that yield neutral solutions. So a salt that consists of a cation of a strong base and the anion of a strong acid will always yield a neutral solution. Let's take the example of NaNO3. The Na plus comes from the cation of NaOH. NO3 minus comes from the strong acid HNO3. So when a strong acid and a strong base react, they result in a neutral salt solution. So this solution will be neutral because neither Na plus or nor NO3 minus will react with H2O to any great extent. Next, let's talk about salts that yield acidic solutions. So to yield an acidic solution, you should have a cation of a weak base and the anion of a strong acid that will yield an acidic solution. For example, NH4 comes from NH4 plus, the cation of NH3, and Cl minus, the anion of HCl, a strong acid. So this solution will be acidic because NH4 plus will react with H2O to produce H3O plus, resulting in an acidic solution. Now, salts that yield acidic solutions also involve so a salt that has a cation, which is a small highly charged metal cation, and the anion of a strong acid also yield an acidic solution. For example, FeNO3 taken thrice, so ferric nitrate has the ferric ion, which is a small highly charged metal cation, and NO3 minus, the anion of a nitric acid. So this solution will also be acidic because the hydrated metal ion will react with H2O to produce H3O plus. Next, let's talk about salts that yield basic solutions. So a salt that consists of the anion of a weak acid and the cation of a strong base yields a basic solution. For example, CH3COO minus comes from the acetic acid, the anion of the acetic acid, and Na plus is the cation of NaOH. This solution will be basic because the CH3COO minus will react with H2O to produce OH minus, resulting in a basic solution. Now, use this principle now. Pause the video right here and try to find out what type of salt or what type of solution will this salt yield, whether it's acidic, basic, or neutral. So pause the video right here and try to solve the problem. Next, let's talk about salts of weakly acidic cations and weakly basic anions. So if a salt consists of a cation of a weak base and the anion of a weak acid, so the pH of the solution will depend on the relative acid strength or the base strength of the ions. For example, let's take NH4Cn, so ammonium cyanate. So you have NH4, which is the cation of a weak base NH3, and Cn minus, which is the anion of the weak acid HCl. So both of them do release a certain amount of H3O plus and OH minus ions, but the relative acidity and basicity, the relative acidity of between the two ions is what results in a certain amount. Notice here the Ka value for NH4 plus and Kb value for Cn minus. The Kb value is much higher, so which means that this solution will be basic. The Kb values, the K values will decide what type of a solution that is present there. So this is the acid-base behavior of salts in water. Next, let's talk about the leveling effect. So all strong acids and strong bases are equally strong in water. So all strong acids dissociate completely to form H3O plus, while all strong bases dissociate completely to form OH minus. In water, the strongest acid possible is H3O plus and the strongest base possible is OH minus. This is the reason why H2O exerts a leveling effect on any strong base or strong acid or strong base. So that here is the idea of leveling effect. So it means that it completely turns into H3O plus or completely turns into OH minus. This is the term what it means as leveling effect. Next, let's talk about the final definitions of acids and bases, the Lewis acid-base definition. So what does Lewis definition say? Lewis definition mostly broadens the acid-base definition. So a Lewis base is any species that donates an electron to pair to form a bond, and a Lewis acid is any species that accepts an electron pair to form a bond. For example, base here will donate its electron pair to the acid and creates an adduct, which is the commonly known as the common compound formation here. The Lewis definition views an acid-base reaction as a donation and acceptance of an electron pair to form a covalent bond. Now, a Lewis base is always the one that must have a lone pair of electrons to donate. So any substance that is a Bronsted-Lowry base is also a Lewis base. While a Lewis acid must have a vacant orbital or be able to rearrange its own bonds to form one to accept a lone pair and form a new bond. So many substances that are not Bronsted-Lowry acids are also Lewis acids. So this Lewis definition generally expands the classes of acids. So let's take a look at a specific form of Lewis acids. Most commonly electron deficient molecules as Lewis acids. So when you take boron and aluminum, the two commonly more often metals as the more commonly the electron deficient molecules are always having an unoccupied p orbital, and they are always ready to accept a pair of atoms. So BF3, when it reacts with NH3, creates an adduct BF3NH3, but this reaction can be considered as an acid-base reaction because the acid here has a vacant p orbital which can accept the lone pair of electrons from nitrogen to create a bond. So this type of bonding is called as coordinate covalent bonding. So this type of bonding is called as a coordinate covalent bond. So it's a form of bond that can act as well. Next, let's talk about Lewis acids with polar multiple bonds. So molecules that contain a polar multiple bond often function as Lewis acids. For example, SO2 can act as an acid because the sulfur can accept a proton, and the oxygen can accept the sulfur can accept a pair of electrons, and the oxygen can accept a proton, resulting in an adduct formation. So the oxygen of the H2O molecule donates a lone pair to sulfur, forming a new sulfur-oxygen sigma bond, while breaking one of these sulfur-oxygen pi bonds. Next, metal cations as Lewis acids. So a metal cation also acts as a Lewis acid when it dissolves in water to form a hydrated ion. So this form of a hydration ion is also the same idea here, that they can expand their orbitals because of the presence of d orbitals. They can use the vacant d orbitals and fill them up with the vacant, fill them up with the lone pair of electrons to create hydrated ions. So the best example of these kinds of hydrated ions, you can see them in chlorophyll with the magnesium ion acting as a Lewis acid in chlorophyll, and you can also see iron acting as the heme in human blood, in hemoglobin. So pause the video right here and try to determine the Lewis acids and Lewis bases in the following reaction. Remember here that the idea here is that the Lewis acid is the one that always accepts a pair of electrons, and Lewis base is the one that donates a pair of electrons. So with that, we end the lecture on acid-base equilibrium. I'll see you all in the next lecture.